For those of you that went on the lab trip last Friday, it was a good trip, and be sure to write up your report by the end of this week. For those of you that didn't get to go with us, please see if you can do a matching experience and do your report as well. In the plant science class, you plant science people, you only need to do a report on post the plant part of it in the plant class, then you can do the animal part in the animal class, or you can just cut and paste them both in both places. That's fine. And that's it for now. Oh, and excuse me, for the state fair trip, I'm going to be sending out a thing early to find out when you're going, because we got to get tickets in advance for it. So the sooner that you let us know, the better. And that's all I have to say.
Very good. Well, didn't get quite through all of the quizzes, but I'm pretty sure that whenever you do the quizzes, someone was asking, they were having computer trouble, couldn't get in to actually get the quiz submitted for whatever reason. Those should, even though the due date is passed, you should still be able to submit the quiz. Again, we'll, let us know what happens. We'll take into consideration any computer issues that you may have. We always tend to have them, right? So, yes. Anyway, on Wednesday, we'll go through all the quizzes, make sure we get a good review there. For today, go ahead and move on to Chapter 4. And just want to remind people, please get online there and just sign up for the crop that you are going to cover for your project. And again, just let me know if you have any questions or concerns about it. Once I have a good feel of what people are covering, I'll go ahead and put up an example of a crop project, at least the report, and we'll move on to the presentation part a little later on. All right, well, let's get into Chapter 4, talking about climate. All right. I guess you guys can see my screen there, right? All right, starting off, what is climate anyway? Well, climate is the prevailing weather conditions of an area, not just the temporary weather conditions, but the long-term weather conditions of an area. Due to the variation or instability in those climatic variables, they might not even correspond to the actual weather experienced at a particular time. So weather, on the other end, is defined by the actual values of the climatic variables and is not the same as climate. So weather is short-term, what you're actually experiencing, whereas climate is kind of more like the average, the long-term average. And I will say on weather and climate, even though we've kind of experienced it for long periods of time, we've only really been recording weather accurately anyway for, about 100 years. Weather records do, in some places, date back further, but, based on just actual observations. It's gotten better with time. We understand the weather more now than we ever have before. So thinking about weather, we have cycles. It changes, right? The climate itself is also it's in cycles. It's cyclical. It does change naturally. Right now we are in I'm not sure how you all are doing over there, but we're in pretty severe drought conditions. It hasn't rained in depending on where you're at, we have scattered showers sometimes, but last time we had rain here on campus that, put water in our rain gauge was 16 days ago. So it's also been unseasonably warm. So generally, those are weather conditions and not, climatic patterns. However, we do know that this time of year, especially when we get into October, seasonally, it's one of our driest months. So going into that, starting off dry and hot is a little worrisome. There's all kinds of climate science going on out there, people trying to think of, how climate is changing, especially in respects to what we've done in terms of carbon emissions, methane emissions to cause the greenhouse effect, which really, I mean, it alters the climate in so many different ways. It's not, remember, it used to be called global warming. It's not necessarily an accurate way to portray it because it doesn't necessarily mean warming everywhere, right? So anyway, I think on the whole climate change front, whether you agree that it's caused by humans or exacerbated by humans or not, I think you do have to recognize that it is occurring. So whether that is a natural cycle and it's just changing because that's what it does, or we've had some impact on it, you can look at the long-term changes in climate and notice how they are changing. And go to the weather websites. They have a lot of this information and the story kind of stored there. So whether it's weather.com or Weather Underground, AccuWeather, a lot of them actually have long-term records that you can look through. And this is really important for establishing, what our growing season is in different places and how we might be able to extend that season to get more crop production. All right. The big thing that really determines, to the greatest extent, the climate and weather conditions is the sun, the solar radiation. It influences all of the other variables that make up climate, and is why we have the whole biome thing, like we were discussing, talking about the ecology, where over areas of latitude, it's very similar. So we also look at how the climate can be modified by local features in a site. So we think of climate, large area, long-term, like for instance, our biome, the temperate deciduous forests, right? So in the eastern United States, that's our biome due to our climate, due to our latitude. But if you look at the changes in altitude and the aspect, whether you're on, a northeast, southwest facing slope or, whatever on the north, south, east, west side of a building, there's little nuances in the local climate. So we look at that very carefully for when we get into production. So we talk about the large scale features such as the continental land masses, the mountain ranges, and bodies of water. They contribute to the macroclimate. So in the mid-Atlantic, we tend to have this temperate climate, 4 seasons. But when we have the smaller effects caused on a site, we look at the microclimate. So smaller bodies of water, buildings, hills, depressions, these contribute to what we call the microclimate. Microclimate is really important to try to learn about in your own site. And the only way you can really do that is long-term observation and making notes about those observations. Microclimate is really important for figuring out, I guess, macroclimate, what crops can grow in our region. Microclimate, when can we grow those crops? So the climate determines the kind of natural vegetation, but it's interesting to note that the vegetation also can affect the climate, and that can occur on a large scale or a small scale. Of course, human activities can often modify a climate, microclimate or macroclimate, and that's inadvertently most of the time, although I guess there are some ways that we've intentionally modified climates, things like cloud seeding, stuff like that. Generally, areas where humans tend to settle are called heat islands because they tend to have higher temperatures than the surrounding area, surrounding environment. mostly due to things like asphalt, concrete. These create thermal mass. Even just, removing vegetation from the soil that have bare soil, that creates thermal mass where heat is stored. And then when the air temperature drops below the temperature of that thermal mass, it begins to radiate that heat back outwards, creating this heat island effect. So things like forest clearance, for instance, tend to lead to drier climates because these trees together in an environment and ecosystem tend to trap moisture, hold it, and allow there to be more moisture in an area. So when we remove that forest, we remove that modulating effect, which leads to drier climates. And on a large scale, desertification. We also look at kind of a more specific type of ecology, where ecology is interacting with the climatic conditions. We call these ecotypes, especially when we're looking at the transitions between ecosystems, which basically allows wild plants and also some cultivated plants to adapt to these subtle differences in the climate. So for instance, one ecotype might have a greater tolerance to cold because it evolved in a specific microclimate. It could be the same species of a plant, but just a different ecotype. We also have these same adaptations in cultivated plants, which by studying that and looking at it, we can improve a plant's success in an area by growing what it's conditioned to grow in. Trying to, we can alter the microclimate to a certain extent. You might have seen things at that organic farm, like adding row cover to an area to kind of reduce that direct solar radiation, maybe trap in a little moisture, reduce insects from being able to get into the crop. That's a little bit of a microclimatic modification. We can't really change the macroclimate, though. The amount of moisture we regularly receive, the prevailing wind condition. We can't change that, but we can introduce things that allow adaptation, whether that's ecotypic or just microclimatic. So as we all know, the sun, of course, is the major energy input for the earth, and it comes in this form of electromagnetic radiation, which to us is light. And when we talk about light, being one of the big drivers of plant growth, right? It supports photosynthesis. So it's just solar radiation on this wavelength. And, most of that comes to us kind of as heat. But if we were to look at the wavelength itself, we actually have this range right here, 400 to 700 nanometers, and that's just the length of the wave that supports plant photosynthesis. This also happens to be the same spectrum that is visible light. You talked about this in earth science class at some point, the whole Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, that when that visible light passes through a prism, we see how it's broken down into the different colors of the spectrum, the colors of the rainbow, right? It's just, that light passing through a prism of water, basically. So it's electromagnetic radiation that we're receiving. We kind of think of it as visible light, but it's more than that. We have infrared wavelengths, which are shorter or I should say they're longer. The shorter wavelengths are things like X-rays, UV rays, etc., that we don't see, but they're still affecting us. Anyway, that's our major energy input and why it drives climate so much. we look at light and its effects as not just quantity, but quality as well. So we look at the intensity of the solar radiation, which is going to be highest at the equator, and it decreases at higher and lower latitudes. But the equator, of course, where it's all equal, they pretty much have, at the equator, 12 hours of light, 12 hours of darkness every day. It's tropical there, right? So the angle of the sun is always close to 90 degrees relative to the Earth's surface at the equator. And then towards the poles, the angle of the approach decreases. So light travels further through the atmosphere, spreading over a wider surface area, making that intensity lower. So in terms of the macroclimate, we look at it on kind of the latitudinal basis, just how the Earth, of course, is tilted on this axis. Which part of the Earth is facing the sun is what drives our seasons. So right now, summer transitioning into fall here, we're starting to kind of spin away to where we're getting tilted away from the sun. Of course, on that autumnal equinox, we'll get that close to, anyway, 12 hours of light, 12 hours of darkness. At one point, we'll have that exactly, depending on where we are. That's the whole latitudinal basis. There are effects, though, within that. So on the microclimate, an increase in altitude. Going up every 1,000 feet, you increase in elevation. The sun's intensity increases by about 1.5 times. So that's just how it affects the microclimate. So here we are looking pretty close to our area, a little bit further north here in Columbus, Ohio, where the light intensity at noon at this latitude is about 60% of the value that it is at the equator. So less light intensity means a difference in the plants that can grow there. And naturally, the plants are adapted to grow at a lower light intensity. We also have all kinds of other things that affect how that radiation is received, like cloud cover. So clouds do absorb a high proportion of the incoming radiation and can accentuate the differences in latitudes. So you can see here over the season, when they tend to have more moisture, we've got cloudier conditions due to that, those bodies of moisture reducing that radiation in the winter months. So the average day length throughout the world is 12 hours because of the Earth revolving once every 24 hours, giving us a day, right? So the day length varies throughout the year because of this tilt, 14.5 degrees in the Earth's axis. And so we have these variations in day length, which add to the effect of the variation in light intensity with the latitude. And when we reach the equinox, the Earth's axis is not tilted relative to the sun, it's even. Therefore, we get that day length of 12 hours kind of right around that equinox. The equinox itself is at different moments for different places on Earth. Either way, that's when we have, in the temperate areas of the planet, the changing of the seasons. And as we know, we also have the solstice, which gives us the change of the other seasons. So at the winter solstice, the tilt is away from the sun, depending on where you're at. And the day length varies depending on where you're at in latitude. This is kind of what creates our natural seasons, but also our growing seasons as well. So, if you're close to the North Pole, then you either have 24 hours of sunlight or darkness, depending on which pole you're at, of course. and which solstice it is, whether it's the winter or summer solstice. But there's a lag in this, and that's due to just the thermal mass of the continents. I mean, the surface of the earth, the land masses actually absorbing that heat or losing that heat. So when we get to December 21st, the winter solstice, it's the shortest day of the year. But is it always the coldest day of the year? It's usually not the coldest day of the year. It's because of this kind of lag. So even though it's the shortest day, it's the average temperatures have been steadily decreasing. And even though the days are starting to get longer right after that, we're still having that kind of lag effect where that heat is still being lost from that thermal mass. So in higher latitudes, of course, winter is very unfavorable for plant growth because there's low or in some cases no light. However, if we look at the opposite end there, we look at summer, cool season vegetables can grow very fast and large in the long, cool days of summer in these higher latitudes, like even into the Arctic Circle. In Alaska and places, they're growing massive cabbages because it's really long day lengths. So they have a very short growing season, but it's very intense. And of course, light intensity is too low. We can use artificial light in some cases to get that photosynthetic spectrum. And we'll talk more about that later on. Some crops, require that. So plants do have this biological clock, and they're keeping track of this duration of light and dark. So some plants will flower or break the buds open when days start to exceed a certain length. Other plants will flower or their leaves will fall when they get shorter. And that response is known as a photoperiodic response. Photo meaning light, and then period, of course, that time. So photoperiodism, and that's how we can actually modify that photoperiod to get some crops to flower, force them to flower in some cases, or keep them from flowering. So the classic example of that, of course, is poinsettias. We grow those often in greenhouses to be sold in the winter, but we have to manipulate the light so that the natural light doesn't cause them to flower early, and instead they get to the perfect size that we want them to be, and then we get that proper 12 hours of light, 12 hours of darkness to initiate their flower production. So those plants that flower when the light period exceeds a critical length are the long day plants. And then those that flower when there's less light are short day plants. Makes sense, then. The photoperiod and the way that it actually displays the difference in the plant itself is called photomorphogenesis, where the actual shape, size of the plant, the way the leaves look are determined by the light quality. And this is all mostly due to this light absorbing protein called phytochrome that causes these different responses, photomorphogenic responses in plants. And really the kind of the classic example of this is sunflowers. They actually do this solar tracking, so their leaves are actually moving to get the maximum amount of light they can throughout the day. So that movement and the shape of that leaf is a result of this photomorphogenesis. So we can see this in greenhouse crops. We can or even in houseplants where they're stretching towards the light. That's just part of it, this response in the plant's morphology due to the light quantity and quality. So light, of course, is one of the biggest driving factors for plant growth because it supports photosynthesis. Of course, water is, the other really big driver of plant growth. And nearly all of the world's water is actually salt water. It's saline, it's in the oceans. So 97.6%. And then of, what's left after that, about 2.1% is locked in glaciers, ice caps. It's frozen. So groundwater actually accounts for only 0.3% of the water on planet Earth. The water that we need is very little amount of it. And only 0.01% actually exists in fresh water in lakes and streams. And then also another tiny important fraction of that, 1/1000% is present in the atmosphere as well. So all of this water and the way that it moves, we kind of refer to as the water cycle or the hydrologic cycle. And it is driven by the input of solar energy. So this becomes extremely important because we really don't have that much water, but what are we made of, right? We're 80+% water. We're like just sacks of water pretty much. When you're doing the lab there on where our food comes from, hopefully it was somewhat startling to you to see that we have like lettuce, which is 99% water, shipped from places like Arizona and California, depending on where you went, of course. So we're just like shipping these little packets of water, which also affects that hydrologic cycle. And in some of these places, I mean, like from Arizona, for instance, there's very little water there already. They don't have much natural rainfall. So we're shipping water from a water poor area to to us where we're relatively water wealthy in a way, kind of altering that cycle. The hydrologic cycle, though, is a global cycle involving evaporation, precipitation. And I would note that water is like energy, right, or matter. We can't create it or destroy it. We can only move it as part of that hydrologic cycle. And here it is. So how does it happen? And it's interesting that we tend to actually practice agriculture in a lot of areas where there might not be as much water. I visited Chile this summer, and it was interesting to see. It was winter down there, of course, in South America. But they're growing a lot of tropical crops, things like citrus and avocados, in a desert pretty much, a lot of grapes. But they have this snow melt runoff from the Andes Mountains, kind of as we see here. Water is stored in the higher elevations in ice and snow. It melts seasonally, runs off. And they have very sophisticated irrigation systems where they're pumping that water from, kind of the bottom of the watershed, these rivers of snow melt, and they're pumping it way up the higher parts where then it's trickling back down. So it's coming from the mountains, they're pumping it back uphill and then allowing it to flow and modifying how it flows through these sophisticated irrigation canals. Why is it so important to grow crops in these desert areas? Well, one of the big things is that humidity, the actual moisture in the air is lower, which means that we're able to grow crops without much disease pressure. The higher the humidity, generally the higher the disease pressure, which, as I'm sure many of you recognize, that growing grapes in our area can be difficult. You need to use a lot of inputs like fungicides because of the high humidity that we have. So we have water stored in the atmosphere. We have surface runoff. We have evaporation from bodies of water and just from surface water, as well as transpiration, which is water coming throughout the leaves of the plants. And this is kind of like the, way that the world breathes in a way, is just this movement of water throughout. Evaporation could come from the surface of a plant, but when we look at it coming through the plant, we call it transpiration. When we add evaporation and transpiration together, we get evapotranspiration. Transpiration is like a plant kind of sweating in a way. It cools the plant to keep it from overheating, and it's also exchanging the gases plants need. We look at evapotranspiration as the sum of evaporation from the earth and transpiration from plants, which is a huge driver in climate and moisture availability. So the amount of water vapor that air can absorb depends on air temperature. And the cooler the air, the less water it can hold, which is why it tends to be somewhat dry on occasion in the winter, because we have cooler air masses. And as that moisture-laden air rises or moves to cooler regions, condensation, that this water vapor, condensing into masses, forms things like fog and mist close to the ground or in the upper atmosphere, forming clouds. When that condensation occurs enough to where that moisture develops into droplets, we get rain, right? We get precipitation. And when it hits the ground, it can penetrate pores in the soil through infiltration, or it can just simply run off. And that is determined by the properties of the soil itself, the topography, how the land is laying, is it sloped, as well as the amount of moisture that is already in the soil. Plants, of course, help to prevent runoff and actually encourage infiltration, one by being a place that intercepts that falling water, and then it kind of channels it through the body of the plant, slowing the passage of that water and then directing it into the soil through the roots. So you'll notice, especially when we start talking about soil, bare soil tends to be a bad thing, because when soil is bare, it allows there to be greater runoff, less infiltration, which causes erosion of the soil, which pollutes the bodies of water and can alter that hydrologic cycle. Runoff, of course, can also carry pollutants other than just sediment, and it may find its way into our bodies of water, these freshwater sources that we rely upon. And if it's not lost by evaporation, then eventually it's going to end up in some larger body of water, usually in the ocean. So depending on where you're at, it might sit in a reservoir or in a lake for a while. Eventually that water will end up, for us, it ends up in the Gulf of Mexico. And for you guys, it would end up there in the Atlantic Ocean or the Chesapeake Bay, right? So groundwater can also accumulate in the natural underground reservoirs that we know as aquifers, which are very important sources for water, for well water. We look at the relationship between precipitation and evaporation as a major factor defining the climate of a region and its suitability for plant or crop growth, especially the natural biomes. So we have light first, then we have moisture that defines what the ecology of an area is like. The amount of water in air is, of course, expressed as a percentage by volume that we know as relative humidity. We can abbreviate that as RH, and that expresses the actual water content relative to the maximum amount that the air can hold at a given temperature, which we look at as the saturated vapor pressure. So humidity, of course, is also a big driver for plant growth. for many reasons. But one is just because of the exchange of gas. When the humidity is really high, it's difficult for plants to be able to transpire. Open up those pores on the bottom of the leaves and let that moisture out and exchange gases. So releasing oxygen, taking in carbon dioxide. So the temperature at which any actual vapor pressure or percentage volume at which relative humidity would be 100% is called the dew point. When relative humidity is less than 100%, the difference between the actual vapor pressure and the saturated vapor pressure is called the vapor pressure deficit. And really that's kind of what's driving that whole process of transpiration and gas exchange. Plants have to be able to respire, actually breathe, actually release that oxygen and take in that carbon dioxide to be able to grow. If the humidity is too high, that will reduce plant growth. And there's a whole lot of math that can be done that researchers look at that relate to evapotranspiration, available moisture in the air, and how that interacts with crops. In general, though, we kind of want the Goldilocks rate of water, right? We don't want too much. We don't want too little. We want just the right amount. And that, of course, depends on the texture of the soil in many cases. If we have really large amounts of precipitation, we have waterlogged soils, that's harmful to crops. So in some parts of the US, we have to create drainage systems to get rid of the excess of water. Successful water management basically involves regulating that availability of water to meet the evaporative demand. So the amount of water that is lost, we have to replace, which can be, pretty significant. It's really important to supply the water efficiently so that enough of that water actually reaches the plant roots and as little as possible is lost. So we can look at irrigation systems. Irrigation is this artificial delivery of water. Some of them are more efficient at providing water. But how does that affect the hydrologic cycle itself? So we have a long history of irrigation, and wherever we had civilization, where there was sufficient groundwater but not enough natural rainfall, we had some sort of form of irrigation. So it allows us to grow crops in areas that otherwise would be unsuitable for growing. Aridosols, the type of soil that tends to be formed in arid areas, can be very productive, even though we tend to think of it as being kind of a sandier soil. It doesn't allow for storage of moisture in the soil. It can actually be very good for producing crops, as long as we can provide that water. So here we're looking at an image taken from the Middle East, where they still have these irrigation channels. And guess what? Lush green growth there. Think about Egypt, right? Or Mesopotamia, these centers where agriculture started. There's sufficient ground flow. We have water from the Nile, for instance, or the Tigris and the Euphrates rivers that allows us to have that water, but we have to move it in order to get it to the crops. So we do that through irrigation. This type of irrigation is through probably some sort of flood and drain. So we have these furrows in the field where water, they fill up the ditches, basically the furrows, and then it spills over into the field itself. Here we have large areas, with overhead irrigation. And one of the downfalls of overhead irrigation, one is that we have to use a lot of energy to pump that water at a high enough pressure to push it out to get it over all the crops. But we also have a lot of evaporation before that water can even reach the roots in some cases. So overhead irrigation is thought of as being somewhat inefficient. We also have, in this case, this is like a soaker hose. You're growing tomatoes here, and it's expensive, right? It's expensive to have this type of irrigation. So generally we see it in smaller scales, more horticultural crops. So we're getting the water more directly to the plant roots through these trickle feed pipes or spray emitters close to the soil surface, reducing evaporation, but getting the plants the amount of water that they need. So drip irrigation, kind of like what is pictured here, is the most efficient form of irrigation in terms of supplying water. But does it actually recharge? If you're very efficiently supplying water to the plant and it's just transpiring, is that actually recharging the hydrologic cycle? So there can be some effects with that.
Ben?
Yes, sir.
Jump in for a second. The lab trip we went on Friday, the organic farm that we went to, they used drip tape pretty much everywhere, and they were doing about 800 to 900 acres worth of crop.
Oh, wow.
Just the drip tape, it's just it's plastic, it's thinner plastic than that hose you're looking at. It comes in rolls, and they put down their plastic, and then they roll this out at the same time before they do their seeding and planting and that kind of stuff. And every bit of what they were doing was with drip tape.
Yeah, drip tape, that's kind of surprising to hear it used on such a large scale. But it has the emitters actually right in the line itself. In some cases, we can configure our own types of irrigation with like the solid plastic tubes and then putting micro emitters in there. The good thing about the drip tape is it's actually in there already in the line itself, so you don't have to alter it. And it's usually spaced at this like perfect 8-inch interval. And you might think, well, we don't space all our crops at 18 inches. Some of them we space at greater distances. Some we might even space much closer, like leafy greens. But if you were to look at the way that water actually percolates in the soil through this capillary action, it actually creates this teardrop that it's touching from emitter to emitter. So that whole front gets irrigated. As we mentioned earlier with the dry areas, an advantage of irrigating is that pests and diseases can be less troublesome for irrigated crops, especially in dry climates, more so than the moist areas where the pests are more prevalent, just due to that naturally available moisture. Another downside of irrigation is that it can introduce salts to the soil, causing salinization, which in turn causes less of that water to actually be available to the plants. And you might not think of it as, well, we're not irrigating with salt water, so why is that adding salts? Well, especially if you're using, municipal water supplies, we have, one, chlorine to sterilize the water to make it safe for drinking. We also add fluoride. Those accumulate and bond to different molecules in the water and in the soil to create a salt, basically. So we actually have large areas of land that have been damaged by salinization. We'll throw this term out here, xeriscapes, where researchers are basically trying to use locally adapted plants to replace those that may be more appropriate for areas where we have good natural rainfall. This is especially in like landscaping. So a little bit here about photosynthesis and the moisture availability. A lot of the desert plants have a different form of photosynthesis known as the CAM metabolism, where they do the opposite of most plants, and they actually absorb carbon dioxide at night. So they're keeping their stomata closed during the daytime, so they're not releasing that moisture throughout the leaves. We also have some warm season grasses that have a similar mechanism, and it's the C4 pathway that reduces transpiration but still maintains high photosynthesis rates in long, hot, and dry spells. So we even have some crops that have this C4 pathway. They're able to produce much more biomass for the amount of water and light that they receive than their other counterparts. So why do we grow so much corn? Probably because it's a more efficient photosynthetic pathway. It's a C4 plant. Same with sugarcane and several turf and forage grasses. So we got light, we got moisture, but how about temperature? This other driving factor, which really drives probably the most important factor in whether we can actually grow a crop or when we plant a crop in a given location. The light creates the seasons, the moisture allows us to actually grow plants, but it's the temperature that really creates the parameters for the growing season itself. So we mentioned the whole idea of that radiant heat loss, the thermal mass. Our radiant heat loss is actually not very much by latitude, as much as the solar radiation does itself, which results in a net energy gain at the equator and a loss at the higher latitudes. These imbalances are the underlying reason for decreasing temperatures as we move north or south from the equator itself. So the temperature is affected by the latitude, of course, but also by the altitude, just as the light intensity is affected. As the elevation increases, our air pressure decreases, which causes the air temperature to drop as well. So they say here 5.5 degrees for every 1,000 feet in dry air, or 3 degrees for every 1,000 feet in moist air. Means that temperate fruits and vegetables can be produced at higher altitudes in tropical countries. Fascinating. Water vapor can also absorb heat radiation so that the cloud cover limits the radiative heat loss, which is very important at night for holding in temperatures. So areas like desert areas where we have very little cloud cover, we have huge temperature swings. As much as, in some cases, 50 or 60 degrees between night and day temperature. Last thing here, looking at how heat is transferred. We look at it by convection, which is the movement by a carrier, important in both the local weather as well as the larger climate. Water and air are the two carriers for convective heat transfer. So we have light creating the heat, and then that heat actually being transferred by moisture in the ground, moisture in the air, allowing that to move. And in some cases, helping us to be able to, grow crops or to actually have a moderate climate. For instance, in Western Europe, it's all because of this moisture or this body of moisture in the air and temperature in the water, creating this convective current that keeps it warm over there. We'll end here just looking at this graph. The Salinas Valley of California being more favorable for temperate vegetable production than the San Joaquin Valley, because it's up to 10 degrees cooler, and that's just due to a difference in elevation. So in San Joaquin, they're growing, more tropical fruits, whereas in the Salinas Valley, they're growing more temperate vegetables. All right, we're out of time. Does anybody have any questions or concerns? All righty, well, go ahead and sign off. Y'all have a good class. We'll see you on Wednesday.
Okay.